All right, so welcome back. Today in this video, we're going to be continuing our Civil FE exam review by going through another topic that's going to be covered in the structural engineering section, which is deflection of statically determinant beams, trusses, and frames. So if you haven't checked out the first video that I made on analysis of statically determinant beams, then definitely check out that one. And I also have videos on every single topic that's covered. So definitely watch those as well. So, all right, so let's dive into this practice problem. Number 1 says calculate the maximum deflection at the free end of a cantilever beam with a length of 5 meters and a point load of 8 kilonewtons applied at the free end. Modulus of elasticity is 200,000 megapascals. Inertia is 0.00045 meters to the fourth. Okay. So let's start out by writing the information that we are given for this question. So we are given the length of beam, all right, which is 5 meters. We were also given that it is a cantilever beam, right? And then we're also given the point load. Point load and the moment of inertia. And elasticity. Okay, is that it? I think that's it. Okay, so what are we trying to find? We're trying to find the maximum deflection. All right, so what formulas might we need? Well, I'm assuming we're looking for maximum deflection, then I need to be in a section that's dealing with deflection, right? So deflection of beams, you could begin to look here, but hopefully you know about this section of the manual, right? This is all information that's given to you, all diagrams that's given to you. Okay, so as you're zooming through, we are looking, I see something dealing with deflection and deflection max, right? But this says simply supported beams, slopes, and deflections. So I don't think I'm looking for simply supported. I'm looking for a cantilevered beam, right? And this particular diagram, right? This one has a point load with a fixed support. This one has a fixed support with a uniform load. This one has a moment at the end. This one has a uniform load that's halfway through the beam. This one has a triangular load. So what are we looking for, right? It's a lot of options. So I think we're just looking for unless we can just draw it out. Okay. From here to here is 5 meters. And I know that I gotta choose a different color. We got we have a load applied at the free end. That's the free end. So 8 kilonewtons. Okay. So I'm assuming that we're going to be needing this first one. There's no uniform load, no moment happening. So I'm going to be using this one. And we are looking for max deflection. So this is the only chart that we should be using is in the deflection. There's also if they ask for elastic curve or maximum moment, then you can use those, or slope. If they're asking you for slope, this would be the chart for you to use. But for our case, we're going to be using this section. Okay. So how do we start this? Well, we know that V max is equal to what? Well, it says V max is equal to negative P A squared, right? All over 6EI times 3L minus A. Okay. So how do we know these values? What's P? Well, P is the load. All right. So I'll just write out all the values that we need that will go into this equation, right? So V max is equal to question mark. We don't know that. All right. What about P? P is equal to, well, P on our diagram is going to be the loading. So I know that that's going to be my 8 kilonewtons. All right. It's the point load. Okay. What about A? A is equal to, it's the distance from your fixed point to the point load. So what will A be? Well, what is this distance from the fixed point? From the fixed support to the point load? Well, that's 5 meters, right? And just something to throw at you, what would B be in this case? It's the distance from the point load to the end. So in this case, B would be 0, but we don't need B in this case, but just a question that, they could ask. Okay. So what is L? What is L? L is equal to the length of the beam, which is 5 meters. Okay. What is E? E is equal to 200,000 megapascals. Okay. What about I? I is equal to 0.00045 meters to the fourth. Okay. Anything else? I think we've written out everything, so now it's just time to plug and chug. All right. So one key thing to note is that 1 Pascal is equal to 1 Newton over meter squared. How do I know that? Well, if you don't trust me, just don't take me for my word, because maybe I'm lying, right? Could be lying. So I've kind of memorized this stuff, but this is why, if you ever get confused, the pascals is just one that you want to know, but you can always go to your unit conversions and then look for Pascal. And here, you can't see that. See if you can see it now. Here, 1 Pascal equals 1 Newton over meter squared. 1 Pascal equals 1 Newton meter squared. So that is in fact true according to this diagram or this chart. So that's why I use it. All right, which section was I in? I was in deflection. All right. So we'll go back to that chart. Okay. All right. So the reason why I say that's important is because you want all your units to cancel. And in order for them to be able to cancel, right, we're dealing with meters here, kilonewtons. So dealing with meters, you're dealing with newtons, and then you're dealing with megapascals too. So to keep everything a little bit simpler, this is meters to the fourth, right? Keep everything simple, just get everything in meters and in newtons. Therefore, your units will be able to cancel, and your Vmax should be, right? Vmax, what is Vmax? Well, it's the amount of deflection that occurs. What's the maximum amount of deflection that should occur from this point load, right? And that distance is what it is. So that's what we're solving for. Okay. So let's plug and chug. So we'll start with Vmax is equal to negative, and I'm putting everything in newtons, and meters. So this is going to be minus 8 times 10 to the third. Why did I say times 10 to the third? Well, I have 8 kilonewtons and I need it in newtons. So 10 to the third newtons times my 5 meters. I'm going to square it, right? All divided by 6. Don't forget that 6 times E. What is E? Well, E is 200 megapascals, or 200,000 times 10 to the 6th pascals. So I just changed it from megapascals to pascals. And remember, 1 pascal equals 1 newton over meter squared. So that should help us out unit wise. Alrighty. What's my I? Right? That was my E. What's my I? I is going to be 0.00045 meters to the fourth. Okay. Times my 3 was L times 5 meters minus A, right? Minus 5 meters. All right. And when I get all this, or plug and chug everything in, I get negative 0.0037 meters, right? Okay. So this one asks me in millimeters. So to get it in millimeters, it's going to equal to, I'm going to take, what's a millimeters? We'll just do the unit conversion here. Right. So should be 1 millimeter, or I'm not gonna try to, I just know it's times, I think it's times 10 to the third, right? Meters. So 1 millimeter is equal to 1 times 10 to the negative 3 meters. And so when we do that, we should get 3.7 millimeters. So that's our units. All right, so I get B for that. pretty straightforward. It's a matter of units. Typically, if you're in SI units, it's going to be newtons and meters. Keep everything in those. And then from there, you can change if need be. If they give you pascals, always get it. If they give you like gigapascals, change it to pascals. And just know that 1 Pascal is equal to 1 Newton over meter squared. So you're still same units cancel. If you are in a UCSC, I believe that's what it is, or American units, basically feet, you're going to keep everything in feet and in pounds. So, all right, let's move on to number 2. So calculate the maximum slope of a simply supported beam with a span of 5 meters and a uniformly distributed load of 2 kilonewtons per meter. Modulus of elasticity is 175 megapascals. Inertia is 0.00065 meters to the fourth. Okay. So what are we given? We're given that it is simply supported. All right. We're given the length of the beam. We are given that there's a uniform load happening, and we got inertia and elasticity. Okay. All right. What are we trying to find? Max deflection. Okay. What are the formulas that we need? Okay. Well, we know that we are somewhere close, right? So I know that this is a simply supported beam. All right. So I'm in the right area now. Literally right up above the cantilever beams. Also, there should be a uniform load that's included in my image. So none of these work, right? This one works, and it says uniformly distributed load. Yeah, so if it's uniformly distributed, it's not half or a triangle, so it's this one, right? So we're looking for the max. I'm sorry. My apologies on this. We're looking for not the max deflection. We're looking for the max slope. All right, so max slope. So as we're going through our process, we're not looking at deflection, we're looking at slope. So slope max is equal to WL to the third over 24 EI. So I'm just going to write that out. Close. Negative WL to the third over okay. And I'm gonna write out all my values. That I'm looking for. So theta max is equal to question mark. W is equal to what? So according to here, my W is going to be the distributed load. So it is equal to 2 kilonewtons per meter. So it's not the total of the distributed loads, it's the distributed load per meter, right? So W is 2 kilonewtons per meter, all the way across. But the W is going to be 2. It's not going to be 2 times the distance, right? Or the length. It's not going to be 2 times the length of the beam. W is just how much ever the load is distributed by. So in this case, it's 2 kilonewtons per meter. Okay. L is equal to what? L is the length of the beam. That should be 5. Right? And then E is equal to 175,000 megapascals. What about I? I is equal to 0.00065 meters to the fourth. Okay. So now, what are some things that we need to note again? Okay, so we plug in everything. We want everything to be in newtons and in meters. So that way our units will cancel. So you need to remember that 1 Pascal is equal to 1 Newton over meters squared. So if we can get this into pascals, I know that everything's in meters to the fourth, meters, and then 2 kilonewton per meter. And so we'll see what that lands us at, but we also need to make sure that that's in newtons per meter, right? All right. Let's go ahead and dive in. So for this one, we're going to say 2 kilonewton per meter, and this is negative. And what I'm going to do is I'm just going to say negative 2 times 10 to the third newtons per meter. So I just changed that from I changed it from kilonewtons to newtons. All right, so 2 times 10 to the third newton over meter. Okay, times my L to the third, 5 meters to the third, all over 24 times E. Okay, so I'm going to put this in pascals. So I know megapascals is always 10 to the 6. So I'm going to say 175,000 times 10 to the 6 pascals. Okay. And then times my 0.00065 meters to the fourth. All right. And from this, I get 9.2 times 10 to the negative 8. So I get a really small number, which is D. All right. Let's look at number 3. This one says a cantilevered beam of length L is subjected to a concentrated load P applied at its free end. The beam has a constant EI throughout its length. Which of the following factors would decrease the maximum deflection, S max, at the free end of the cantilever? Increasing the length of the cantilever, increasing the magnitude of the point load, increasing the EI of the beam, or changing the location of the concentrated load to the midpoint of the cantilever. Okay. Alrighty. So let's look at this. We are looking at, let's write our givens. All right. So given we have a cantilever beam, and we have a constant EI, which is modulus of elasticity and inertia. All right, it's not a changing. When those change, that means you're changing properties of like going from maybe steel to wood or something like that. So that's what that's saying. Okay, so find, what are we trying to find? We're trying to find which of the following factors would decrease max deflection. Okay, so let's just look at this. What formulas might we need? Well, let's look at max deflection, right, for a cantilever beam. Okay, so we're still in the same section, but we're looking at deflection for, is this for a point load? Concentrated load, yep, P. Okay, so we know that V max is here. All right, so V max deflection is equal to negative P A squared over 6 EI times 3L minus A. Okay. And so even with, this is a conceptual question, but sometimes you can use formulas to understand the concept, right? So in this case, I'm going through each of the, I'm going to go through each of the choices and see which one will decrease the max deflection, all right? So if I increase the length of the cantilever beam, right, I increase L, what happens to this whole equation, right? Well, if I increase L and everything else is 1, then V max, so I'm gonna just do it up here, V max would increase, right? And so I don't think it would be A. If I was to increase the magnitude of the concentrated load, that means I take the same equation, and instead of making, we say every A is 1, E, I is 1, L is 1, A is 1, and I just look at primarily P, and I increase it to 2, right? when I do that, my Vmax again increases. Okay. What about increasing EI? Okay. So if I increase EI, all right, I say everything, say A is 1 and L is 1, but I increase my EI to 2, then my Vmax decreases. And then if I change the location of the concentrated load, P, to the midpoint of the cantilever, would that increase or decrease my Vmax? Well, it depends on where it starts, honestly. But the best answer would be C. All right. So that concludes deflection of statically determinate beams and trusses and frames. And so in the next section, we're going to be looking at column analysis. See you in the next video.